for the invitation and for giving me this opportunity to present my talk here. So today I'm going to talk about matrix factorizations from Fukaya category of surfaces. So main goal is to explain some concrete examples where we can explicitly benefit from the homological mirror symmetry through the study of matrix factorizations and Cohen-Macaulay modules. So this is a joint work with my advisor, Cho-Jeong-Kim, and another collaborators, Cho-Jeong and Cho-Jeong-Kim. But if you have any questions or comments, please let me know anytime. So I would like to begin with some review of Burban-Drozd classification of this matrix factorization. Actually, it works also well with the singularities like x plus xyg for p greater than equal to 2 or this. So all of them define some non-isolated surface singularities, and actually Igor Burban already explained in detail how they did classification in, in more general cases. But for this talk, let me focus only on this XYG examples. But the content of the talk will be in principle just applied to this kind of singularities as well. So for these matrix factorizations, I will consider the singularity or commutative ring A, which is our third ring of three variables, quotient by a single monomial. So geometrically, it defines the affine scheme, which is the union of three coordinate plane in three-dimensional space. And the singular locus looks like this union of three affine lines. And related to this singularity, we can associate many interesting categories, especially triangulated categories. Which all turns out to be equivalent. So first, we consider the singularity category of A, which is by definition given by quotient, which most of the audience are familiar with. And the second one is the category of Cohen-Macaulay modules, which appeared several times in this conference. But here, to make it time-directed, I take some stable category, which is by definition given by the original category, quotient by the free module A. Quotient by this free module A. It's free and also Cohen-Macaulay. So the original category gives with some provisions category structure, and you can take a natural stable category like in this way, modulo projective object. So it becomes a natural triangle. The third one is like in the title, matrix factorizations of x, y, z. But again, I take some decoration like homological category or also some stable category, which you can understand by modeling out only two trivial objects in this category, which would be 1 times xyz and xyz times 1. So these stable categories and the original categories are not that very different in terms of classification, because we just model here one object and here just two objects. But actually, these categories are all equivalent. So in terms of classification, if we just this to classify one, then we get all classification. So let me mention this equivalence was first observed by Fukaya already in 80th century. 80s. Not in the future. And this one was done by Abouzaid-Auroux-Efimov-Katzarkov-Orlov in the same century and decade. After 2 decades, the equivalence of singularity categories and matrix factorizations were rediscovered by Rho, and he also generalized these two global singularities.
Sorry, why the two previous identifications don't imply the Orlov one?
Yes, actually, in this local case, yes. But if we go to more global singularities,
so the theorem of Orlov is not for this case; it's more.
It includes this. Actually, in his paper, he said that he didn't know this works. And I don't know. Maybe it would be independent from the other works. But of course, this equivalence comes from the combination of two works. So they are all traditionally important categories, and to classify objects here, Burban-Drozd introduced a new category called category of triples, which I will not I will give some elements later. But anyway, here to make consistent with other ones, I omit only one object, TA, which corresponds to the free modular A here. Now we have another equivalence. Burban-Drozd. 1727. So to record the theorem of Burban-Drozd, the benefit of having this new category is that in this category we can control the classification in terms of so-called matrix problem, which is sort of linear algebraic problem, and they classified or indecomposable objects, which falls to two types. First, bent type, which continuous families. And another one is string type, which consists of discretely, countably many objects. And as a result, it turns out that this category is representation K. Not finite, not discrete, but the two immediate terms of this continuous family is term representation. Also, other equivalence categories. Moreover, they gave a full classification list in terms of some range data and string data. But today, I will concentrate only on range type. But string type can be done in a similar way. So, think about range type indecomposable objects. They are parameterized by range data, which are triple of three independent parameters. So first, W is a sequence of some integers. Of range 3 tau or some tau. It's called as a band word. And the second parameter is the continuous one. So lambda is an element of C star, which are uncountably many. I will call this as an eigenvalue. And the last one is again a discrete parameter. Mu is positive integer, for multiplicity. These parameters define band data. Let me explicitly write down the corresponding object in the table of the papers. So for each band data, we can associate an object which set in the category of triples, which is a decorated representation of some hexagonal figure. Let's assume for simplicity mu is 1. Then we have 6 vector spaces over Laurent series field, which forms this kind of hexagonal figure. And there are 6 gluing maps, which are linear maps between for each arrows. So here I will use notations like I plus would be the positive part of the integer li, and Li minus is the negative part. One of them is just 0, and other is a positive number. Likewise, we define mi plus minus and ni. So given this integers, we associate some diagonal matrix. Here. Draw the 5 diagonal matrices. But if the other one is again diagonal, it must be decomposable. So we make some cyclic permutation. So here, I rather draw 2 plus 2 half plus yes.
Yeah, maybe I have one stupid question. So could you do this kind of in three? Some field other than C?
Yes.
Any algebraic kind of fields?
The formalism was over any field, but for this classification, I will choose algebraically closed field. But there are still theories where you can use any field. You will see why soon.
So 1 lambda is missing.
Yes, exactly. We used all band data, band word here, but lambda is missing, so it should be somewhere. Here, I put my lambda. Okay. And actually, for general mu, the matrix form is similar, but we make it bigger by changing it to tau mu by making some block diagonal matrix. Everywhere I insert the identity matrix of size mu. It's not interesting, but here instead of lambda, I will insert j mu lambda, which is the Jordan form of eigenvalue lambda of size mu by mu. Actually, we need this algebraic closeness of the field to get this classification. Otherwise, it becomes a little bit more complicated. Any other questions? Okay, so we already have a very beautiful classification of category filters, and at the same time, Cohen-Macaulay modules and matrix factorizations. But still, we can raise some questions like how can we intuitively or somehow geometrically understand this classification. Right? It's quite complicated, but we want to analyze it, where does it come from geometrically. And Another one is to we have a canonical form related to band data in the category filters, and you can find the corresponding Cohen-Macaulay modules using the reconstruction procedure given in the same paper. But still, the corresponding canonical form or normal form, in terms of matrix factorizations, has been missing. Because in the category of matrix factorization, we have another benefit of writing every object in some explicit entries of matrix. So far, okay. Using only this description is not that easy to find the corresponding canonical. And from now on, I will answer these questions by using some insight from homological mirror. Okay, so now let me review a little bit of homological mirror symmetry relevant to these categories. Here I have some Fukaya category of this equivalence surface and equivalence with the table of matrix factorizations. So this kind of mirror symmetry was first proven by Abouzaid-Auroux-Efimov, and Katzarkov, the previous speaker here, and finally Orlov. There they considered as A model some selected surface, and as a B model some Landau-Ginzburg models. So starting with the simplest one, here we have this three-punctured sphere, which is also called a pair of hands. On the other hand, in the B side, we have some singularity given by x, y, z equals to 0 in 3 space. So they showed that this mirror pair, and likewise you can generally consider some higher punctured surface. For example, for punctured sphere, the corresponding edge model or the singular space is given by some gluing of these two normal crossings. So one x, y, z equals to 0, and another piece of x, y, z equals to 0. I will come back to this point in the final part of my talk. So far, let me continue to speak about this local model. In general, we have this kind of mirror of any punctured spheres, and on the right hand side, that linear. So There's some gluing rule given by x prime is 1 over x, y prime is y, x, y, z prime is x, z. So this is a gluing of two affine schemes along with their intersection. But
This relation.
according to this relation. But I will give more detailed description of this gluing.
Okay, thank you.
Yeah. Thank you for the question. So here, at all, we have an equivalence. So let's say this surface is sigma, and the singular space is x. Then we have a equivalence between the derived rep Fukaya category and the category of singularities of x as triangulated categories.
So in the second line, you only have the singular locus of x.
No, actually, we consider the whole space.
That's a surface.
Yeah,
Okay,
yes, I omitted here. So, of course, I'll just do the singular locus. Anyway, we consider the singularity category of the for a normal crossing surface singularity. It was first given by some toric variety, explicitly constructed from some toric band construction. But for these cases, it can just given in this one.
Now the situation is global. So X, when you glue several pair of points, the situation is global, and all these theorems by Eisenberg and by were local or they were global?
They were local, so they doesn't apply to this situation. But we still have some notion of matrix factorization, global matrix factorization over these singularities due to Orlov.
And the version for singularity category that you take now is matrix factorizations.
Yes, in the sense of Orlov. He also showed appropriate matrix factorizations over this global singularity is equivalent to the pure singularities. So here I was speaking about this. And for the purpose of comparing and classifying the objects, we need another elaboration of this mirror symmetry due to Cho and Cho-Hong and Cho-Jeong-Kim-Rho. So Cho-Jeong already gave a very detailed explanation of this homologism. Just for recall, I just mentioned that there was a special kind of program here, which out so that the disk potential of L is exactly given by our desired polynomial xyz. From this, we can construct an explicit functor with a reference L, both L, from the derived Fukaya category to the category of matrix factorizations. So it again realizes this homological mirror symmetry, and in this case we have a explicit functor, which means now we can compute or translate object in the Fukaya category into the explicit matrix factorizations. So we call it localized mirror functor. Because it applies to this local model and later can be glued together to make the corresponding functor also in this case, as Cho-Yeon explained in the last part of this. Anyway, let me still continue on this local model. So briefly remind you that we have some nice correspondence between curves in the category. Let's say this is L1, this is L2, and this is L3. Two of them generate the Fukaya categories. And this simple Lagrangians or curves converted into also some simple matrix factorizations. But they are too simple to represent the whole complicated objects obtained in this category of types. So the way to make more examples of matrix factorizations is also to consider more complicated curves. For example, they do not have to be simple anymore. Just, well, can be complicated in an arbitrary way. And we can compute the corresponding matrix factorizations from this immersed Lagrangians. So for this specific example, I will just write down just for fun. As we learned in yesterday in Cho-Yeon's lecture. You can just check immediately response matrix factorization of xy. Right. So it's again just an example. So we know now we can consider many arbitrary loops to make somehow complicated objects in the matrix factorization. Let me keep this and erase this.
Question maybe is completely stupid. Any homomorphic group, any loop can be realized as a Lagrangian.
Yes, it's a very good question. So that is on part of our observations. So let me write down. Right. So now. Get more complicated examples of matrix factorizations. We consider any immersed loops with some with a local system, which I will explain now. So here we introduce the notion of loop data consisting of W prime, lambda, and mu in a very similar way with the web data. So here again, W prime is a sequence of some integers of length tau, which we call loop word. Okay. And lambda is again a continuous parameter. It's just an element of this system. It's called the holonomy parameter. And finally, mu is a natural number called the rank. You can find that this is very analogous to M data. And associated with this data, we define an object of Fukaya category. So first, L, which depend on the chosen loop word, is a immersion of S1 to our surface sigma. This is immersed oriented closed curve or loop. Okay. I will explain it. So we start from here, and according to this loop word, so I visit this hole and lap around it L1 prime times, and goes to the next hole and lap around it M1 prime times, and goes to the last hole and again lap around it N1 prime times. But it doesn't go directly to the starting point if we have longer data. Then we again goes to the first hole and wrap around it 2 prime times. And then goes to the second function and left it M2 prime times. And then after finishing tau round, and after the third function and tau prime times, it goes to the origin point. So it should be mi times, right? Mi times. Okay. But it looks like to be complicated enough already, but still it doesn't represent the continuous parameter, which should be there. So for that purpose, we also consider some vector bundle. I will say it's a trivial vector bundle of rank mu. Mu trivial vector bundle on the domain of L, S1. And then consider a flat connection on E. And due to the dimension, every connection is flat, but is common in our category. So let's stick to this notation. And whenever we are given a flat vector bundle over S1, because its fundamental group is generated by one element, we can just think of the holonomy. I mean, along the group. It will give a matrix in CL mu of C. So according to the chosen holonomy parameter, we force the holonomy to be the Jordan block of eigenvalue lambda. So these two define equivalently local system on L. And actually this triple, which I denote by calling L of the corresponding loop data, is an element of our left Fukaya category. Which means that we can convert this object into the corresponding matrix factorizations under the localized mirror functor. And after all, we can summarize the results as this. We have two papers on this. The first one is to work in Cho-Rho, and the recent one is Cho-Rho. Basically, in the first paper we did with the rank 1 case, and this year we generalized it into arbitrary rank, considering a higher rank rank of this. So first, we prove that each loop with a local system gives a well-defined image denoted by phi of the same loop data in the category of matrix factorizations. So here, actually, if we consider just arbitrary immersed-oriented curve, the traditional Fukaya category theory doesn't guarantee that the coefficients lie in our field C. Rather, it's in the Novikov field. So, well, if you consider some exact curve, you can avoid it. But here, I'm considering more arbitrary curves. So we need to develop some geometric techniques. After all, we concluded this has to be immersed curves is a well-defined image over C, not over the Novikov field lambda. If you don't know this, we can just do it. And
So this means that if you are not careful, you can then over lambda, but you need some extra geometric work to reduce to C.
yes, if we consider some oblique curves, sometimes it gives infinite terms in each entry of matrix factorization, which will not lie in matrix factorization over C. But we have some control of our loops. This technical.
So in general, when you start with the curve, you obtain a matrix factorization over lambda. This is what you.
Yes, always we have lambda over lambda, we have good motion. But here, I really wanted to restrict to C, because it is developed over C for arbitrary space. Anyway, and the image is invariant under the homotopy class of the underlying loop L. We don't have to worry much about this. And the HKG equivalence class of our local system. Okay. But still, you have to know these kind of things, and all objects in our categories. So that we make this statement. So instead of group data, and
But can I ask a bit more?
yes,
In which sense the matrix factorization over lambda is an element of the category, the singularities category?
ah,
Because you said that the functor goes from Fukaya category to singularities category.
right. Functor goes to matrix factorization. And here you take the co-comma and it gives an equivalence with Cohen-Macaulay models. And you can just consider this as a second class in the derive category. I mean, there's a functor just then singularity over A.
But where is another topic?
Well,
I don't see how to.
we already omitted the existence of
No.
non-decouplings
No,
here.
but my question is if you are not careful,
Ah,
by choosing the curve, you said you get to a matrix factorization over the novel coupling.
I see.
In which sense this belongs to one of the categories that you wrote there? Because you said that the functor is to these categories. And then I
Yeah, we can then define this category matrix factorization over the Novikov field, which would be a primary from DG category, and take the homotopy category there.
and then the localized mirror functor in fact ends there.
Yes, before we take the homotopy category, it defines a infinite functor from the Fukaya category before taking this derive to the DG category of matrix factorizations, which considered as a infinite category.
Another primitive question about this. So this matrix factorization seems like it cares about the embedding of this hypersurface to C3. But if you, whereas the other ones don't, is there?
What do you mean by the other one?
Was the Cohen-Macaulay category, the derived category of singularities? They don't depend on the fact that you're stuck with three variables.
It does. It is actually the category of Cohen-Macaulay shifts over the corresponding scheme defined by.
Yeah, but that's the scheme locus, yeah. Whereas I can imagine you can factorize you can have two matrices where other variables appear, but when you multiply things cancel, and that those extra variables do not appear. Is that the same matrix factorization category?
I didn't get it actually.
The matrix factorization category depends on the scheme given by xyz equals 0, or depends on the polynomial xyz on C3?
It can be just defined with respect to polynomial. There, we don't have to speak about schemes.
Yes. Therefore, my conundrum. The other two only depend on the scheme defined.
Oh, no. A was our commutative ring, defined as this quotient. So here I'm just considering a module over A, satisfying some conditions.
Yes.
And the singularity category is also defined as derived category of A modules, which doesn't, depend on the geometry, quotient by the first category of object complexes.
Yes, but my question is that MF seems to care about the polynomial being in three variables and not in four variables, one of which you don't see.
For sure.
Yeah.
Because
I have to
it
then
should. Well, so you cannot add any new variables. So it's not your convention when you speak about the stable category of matrix factorizations.
Okay, it was my laziness not the ambient rings. I consider matrix factorization. Yes.
Related with the question of zero, that for example, if you replace x by x times a new work, then the scheme is the same, but the expression xyz is not the same.
So yeah, it depends on the ambient effect, I would say. Whether if you take the power series or polynomials given, and if you add one variable, maybe it will not be equivalent anymore. So I fix or locally. Yes.
So it's not preserved on the change of coordinates. The matrix factorization category. That is related to the question of Merton.
To be honest, I think not talk about it.
It should. Well, I mean, the question has to be made precise, but in appropriate sense, of course. But here's a question was what happens to the category if you add new variables? Because it changes drastically.
Okay, then what is the equivalence of Eisenbach? The equivalence of Eisenbach says that you shouldn't change.
You fix a polynomial here.
Yeah, but CM does not depend on.
So that's probably that the Eisenbach is a time, and there is no inverter.
But CM depends on what variable data and isolated.
So maybe this goes in a time with the not in the loop.
But it's nothing variable.
Okay, I think I sorry, I didn't have a question.
So, we just start with arbitrary natural locally and just pick any non-zero element f and then take the quotient. And the Eigenvalue theorem works well for this area. But I don't know about the coordinate change. So, anyway, to achieve this classification, we have an one-to-one correspondence between loop data and band data, such that they have compatible conversion in each category. So we start from poly L associated to the loop data, and it defines corresponding matrix factorizations. And taking the co-kernel or under Eigenvalue theorem, it defines some Cohen-Macaulay module. But here we use the one-to-one correspondence here, which we call a convergent formula. So this is described by band data. Anyway, under this correspondence, we have this correspondence in tables. And finally, we can again convert it to a table of triples, which land in this object. So one other point is to the second question is that now we can compute the corresponding matrix factorization, which we call the canonical form, corresponding to Burban-Drozd classification. For this, I want to mention the opposite way is not easy to compute because you have to consider some algebraic procedure for the macqualification, and here you find some screen resolution, which is not very easy, but once you have this candidate, converting it to module is relatively doable. So that's how we obtain the canonical form of matrix factorizations corresponding to this object. And also for the first question, we found some explicit geometric object here corresponding to algebraic object. So more things, so let me just mention so that after this correspondence, we have some one-to-one correspondence between closed geodesics in hyperbolic bench, the decomposable bench type Cohen-Macaulay models, which gives another intrinsic formulation of our theorem. We'll speak about that. And there are some explicit applications. So which exchanges some geometric symmetries here and algebraic operations in the algebraic categories. For example, to compute the shift operator in Cohen-Macaulay modules or so-called Auslander-Leiten translation is not so easy only in terms of band data. But geometrically, we can relate the operation to just changing the orientation of the underlying curve, which we can do it very quickly. So we can do it in loop data. So now we have a systematic way to compute so-called triangulated structure. Also, some mapping cone operations here using geometry.
So, Kyungmin,
Yeah.
there is a compliance that you have not considered strings. Inside is an equivalence.
Yes, actually, here I considered the loops, which is compact object, but we can also consider this some arbitrary arcs, which start and end from functions. They correspond to string object, and there we don't have this polynomial parameter because we always write the gauge equivalent to the trivial ones. That's why we have only discretely many string objects or arcs. But does it answer your question? Finally, I will describe some strategy to make this more globalized. So for this, I used the mirror symmetry of pair pens with some singularity category, which I will denote by x. And one simple observation is that x, which is given by the spectrum of x, y, z, is realized as a colimit in the theory of affine schemes of this hexagonal diagram. Here you can think of it as gluing of three affine planes, x, y, y, z, and gx planes, along with the x, y, and g axis. So after gluing that all together, we have this normal crossing singularity x, y, z equals to 0. And we found that this geometric realization of x is closely related to the construction of the triple categories, where you observe the representation of very similar hexagonal figure. So here, the singular locus looks like this. And finally, in the four-punctured case, we can also exploit from the mirror symmetry of functions here with singularity category of x union x prime, which just formal notation can be explicitly realized as the colimit of more irreducible components. We have a similar conclusions. And the observation is that this gluing of more pieces of varieties gives the corresponding single zero locus of the random interval model. So here I can do the singular locus in this way. So this piece is P1 and other ones are affine lines corresponding to this. So it defines another normal crossing global surface singularity, and well, we can do the similar thing. So Cohen-Macaulay sheaves over this global scheme is equivalent to some category of triples corresponding to this fluid quiver, because if you split it into two pieces, each one represents the previous hexagonal diagram. Likewise, we can much more generalize it into arbitrary generous Riemann surfaces, and can do the similar thing we did here. So it gives another sort of matrix problem, which still I didn't make it to classify, but I hope to be able to do it. So let me stop here.